Hi everyone, this side Abhipsha. So let's just start with the AI/ML session. So before that, I just want to welcome all of you in another session of AI/ML. So as discussed, we will be going down in details with the models like in collab. So we have completed some part of it in the last session. We'll continue from there. So we'll just take a recap of that so that things are clear to you. Whoever is seeing in continuation, don't face any issue. Okay. So fine, guys. Just let me share my screen. Okay. Hi, everyone. Welcome in another session of AI/ML. So before that, let me just share my screen. So we will be continuing from there where we have stopped. Okay, so that things are accordingly understandable to each one of you. So I have just presented my screen. You can see it. Hopefully, my voice is clear to you and my screen is also visible. Okay, so we'll just take a recap of the first part so that things are easily understandable by you and you can just correlate with it while we will be moving ahead. Okay, so we have just gone ahead with the K means. So we have got a lesser value of Laute score. So we want to increase it. So we'll just start from beginning only. You'll be able to see what are the steps and stuff so that things are coming down in a proper continuation so that you can understand it. Okay. So first we have imported all of the necessary libraries. First we have taken imported NumPy as NP. So we are bringing the math helper library here in our program. So NumPy actually helps work with numbers, arrays, and mathematical calculations. Next, coming down, we have pandas. Then that is basically help us to work with the tables like the Excel sheet. Sorry, guys. Then we have used the matplotlib and cboard that are basically for the visualization purpose. Guys, just a moment, please. I am just continuously having the cough. Just a moment, please. Okay, guys. So then we have taken, like we have just imported the load rest. So load iris basically. So we are asking for this ready-made iris data set basically. So sklearn that is actually the machine learning toolbox you can have that contains the model, databases, evaluation tools, all of them. Okay, so that we don't have to write each of the code from scratch, right? Now we have this Irish data set. It contains 150 flowers record. There are basically three types of flowers that is Setosa, Versicola, and Virginica. And each flower has sepal length, sepal width, petal length, petal width. So we are loading Iris that gives us this data set instantly. We don't have to just take it down in the Google Drive and then need to collect it. That is a huge problem. So this some of the data set are there that we can access accordingly. Not all, but some we can definitely do. So Iris data set is one such type. Okay. Then from sklearn.cluster import k-means. So we are bringing the k-means algorithm for like basically for loading our data and for modeling basically. And then basically we are going for sklearn.pre-processing, that is standard scalar and label label binarize. basically label binarize, really sorry, yes, label binarize. Basically, standard scalar is for making all number into the same scale, that is height, weight into the same scale, and this label binarize that actually converts the labels into the system understandable format like 0 1 format. Okay, so it actually converts the labels into 0 1 format. Okay. Next, we are importing the Silhouette score, confusion matrix, accuracy score, ROC curve, AUC, all of them. So Silhouette score tells how good the cluster is. Confusion matrix is for showing right versus wrong prediction like TP, FP, TN, FN, all of them. Accuracy is the percentage of correct answers that we are getting. ROC curve is create a point for ROC graph and shows the trade-off between true positive and the false positive, and AUC calculate the area under ROC curve, one number summary performance basically. Next we have from scipy.stat import mode. That is basically we are importing the mode, finding the value that appears most of the time is the mode value basically. So that is what we have imported in the library section. Okay. Now going down with the loading the Irish data set. There basically we have used Irish equals to load underscore Irish. That simply means bringing the Irish flower data into the program. So what is this load underscore Irish? This is a ready-made data set that we already discussed, already stored in scikit-learn. Now uh, we have included iris. What is iris? Iris is like iris is the basically the data set, the name of the data set that contains the flower measurements, the flower names, the flower features, and the class labels. Okay. So now x equals to iris dot data. That simply means like we want to take the numbers, that is the measurement of the flowers from the data set in x column, like under the x, and y that like because x is the input and we will use that would be used by the model for learning the patterns. Okay, so it will look on the flower size and shape and decide its group basically. And why we are typing as like trying it as iris dot target. So that simply means taking the correct answer. So iris dot target, that means it contains the labels, right? So the labels are Setosa, versicola, versinica. So 0 1 2 like this, it will be taken because 0 1 2 why? Like why we are encoding that? Because my models won't be able to understand the categorical type like Setosa, versicola, versinica. That's why it is changed. It would be changed to encoding. Like we will be encoding it. So Y is basically the answer key. So that is used to check the predictions are going correct or not. So that's why, and also Y are the labels when we will be when we will be dividing the data into training and testing. In the training, it will contain the X and Y, X train, Y train, it will contain. That would be given down to the model for training so that they can just from the right answers, they can get the correct, they can learn it accordingly. Feature name equals to iris dot feature name. That simply means get the names of the columns. That is the idea. So what is this feature's name here? It would be sepal length, sepal width, petal length, petal width. And we have got the target names that is equals to iris dot target underscore names. That means we are getting the actual flowers name there. Like what are the actual flowers name that are getting stored in target names. Okay. So here we are getting basically the numbers that is 0 1 2. So we will get like here like target names. We won't be getting the numbers like 0 1 2. We will be getting directly the names that is Setosa, Versicola, Versinica. This helps humans like us to get the understanding of what is it like 0 1 2. If this is how the labels will come, we won't be understanding. Like we don't know internally how my system has taken that, right? So that is for that purpose. Next, we have taken def equals to pd dot data frame. So that actually turns the flower numbers, what are the datas or the matrices we are having, into a table format. Okay. So now we are doing df actual label equals to y. Add like this actually add the correct flower type as a new column. Okay. So actual label, the name of the labels we are getting as the column name we are getting as actual label. So we are creating a new column. The name of the column, like let me just give you the idea. So how the new column looks, it is actual column, sorry, actual label. Like this is the actual label. Okay, just a moment. Actual label. Okay. So this is the name. So now here we will be getting stored as 0, 1, 2, like this. Okay. That means suppose 0 means Setosa. Next, suppose 1 means versicola. Versicola. Next, we have Virginica. Like this, it would be coming. And my entire data set is sepal length, sepal width, petal length, petal width. Right? So here it will give some of the numbers like suppose 5.1. Next we have 3.5. Next we have 1.4. 1.4. Next, we have 0.2. Like this, it will come. And then, along with that, we have this new values, like this new column, like Control C, Control V, this one, this column name. And here it will be stored as table 0, then suppose 1, then suppose again 0, then suppose 2. Like this, the values will be storing. And here also, the values will be stored like this. Okay, so this is the entire thing. Like, hope you have understood. Like, let me just give you the idea. Like, let me run it first. So it's taking a bit time to because I haven't run it before. I have to run it once more. Like last time we have just discussed and then I have just switched it off. Like that's why. Now here you can see that it has came up like that. Now here suppose I am using df dot head. Okay, what's happened? Right now, let me run it. Now you can see the actual label. Like here, you can see a column that is actual label. The way I have showed you, the same thing you can see it here, right? So sepal length, sepal width, petal length, petal width, actual label, all of it are here. Okay. Now after that, what I am doing the feature scaling. Feature scaling that means we want to scale the features. We want everything in a same range. All of the measuring points should be in same scale. That's why. So scalar equals to standard scalar. That is, we are creating a number balancer machine basically here. So standard scalar that actually makes all numbers similar in size and remove all of the if any numbers is coming down in an unfair advantage, like is getting unfair and advantage because of the higher value of it, so or for the bigger numbers in it, so that removes the unfair advantage of big numbers. Okay, so that is the part. Next, basically, it is coming down and doing x underscore scale, that is equal to scalar dot fit underscore transform x. So here, basically, fit x fit Fit X is another one part and transform X is another part. So it's doing the two job together. So fit X is coming down in my learning step. So that look at the data and learn how big and small the numbers are. So what does it learn? So from each column, we are getting the mean, we are getting the standard deviation. Mean is the average, standard deviation is the spread. So the sepal length average that we are getting, suppose here, let's just take sepal length average AVG, we are getting as suppose 5.8. And the spread we are getting, that is standard deviation, that we are getting it as around suppose 0.8. Okay, so this thing is getting found here in case of fit. Okay, and then we are getting transform. Transform is the form of changing the state. That means use what you learn to change the numbers. So this thing has been learned in fit X. Like my total section, if you can see here, my total section is fit. Okay, just a minute. Fit underscore transform X. Right. Let me write it here. Right, this is my part. So we are actually taking it in a form that we are just getting it in a two forms. Like we are just getting here fit transformed x means fit function plus we are taking the transform function together. Okay. So as discussed, what we are doing in case of transform basically taking it like changing the steps. So using the whatever we have learned to take it another way down. So I'll get a new value. That is what is the value like for the transform? We are getting the value that is coming up. New value is coming up. That is old value minus mean divided by standard deviation. That is the value. Okay. Suppose I am getting my mean height, mean height that is coming out around suppose 100. Standard deviation is coming out suppose 10, all in centimeters. Okay. Because my measurements are all in centimeters. So a child's height, what it would be? A child height would be like just for a reference, I am taking child's height, but here it will be the petals. So that is suppose around 110. Okay. So now this is my old value. Now how I am doing 110 minus 100 divided by 10. So this is giving me what? This is giving me 1. So my new value is 1. Like after scaling, this value will be changed to 1. So after, because when I am scaling it, I am just getting, suppose this 0.8 would be changed with 5.8 will be changed to somewhat value around, suppose 0.8. I will get the value between 1 to 0, right? So here, my value for the child height is suppose 110, right? So I am following this formula to get the new number with what it will be replaced after scaling. So my with 1 it would be replaced after scaling. Okay. So fit transform that as I told, it is taking fit plus for transformation together. That is faster and making it clear. Okay. Okay. So X scaled basically have the same shape as we have in X, but the values are now centered around 0 and more balanced. Okay. Suppose before my values, but like before scaling, if my values are suppose 5.1, 3.5, 1.4, 1.4, then suppose 0.2, like this my values are. Then here, in case of after scaling, it will be changed, suppose with 0. Minus 0.9. Then it would change to 1.2. Then it will change to minus 1.3. Next, it will change into minus 1.4. Like this, the value will be changed after scaling. So why scaling is super important? Because K means uses the distance, like the Euclidean distance, as you all know. If one feature has higher value, another has smaller value, then the bigger number will dominate, right? right? That is the reason we are going for scaling and fixing this problem. Okay, so this is how my values are coming down. Hope you understood what we have written up. So we are not going in details on that. Now coming down here, so this is the part. Now what we are doing, we are using the elbow method. Okay. So before that, here you can see we have used inertia. What is inertia that we need to understand? So inertia tells us how messy or neat our data or groups are. So it tells us how messy or neat our data groups are. So messy group that is higher inertia, neat group that is lower inertia. Okay. So we have already discussed about WCSS, right? So that we can like collect it from there, and the basic thing is that only. Okay, the same thing. So student, suppose student is the data point and teacher are the cluster center. So inertia is the total distance of all points from their cluster centers. Okay, that is coming down as inertia. Okay, so we have discussed what happens when k equals to 1, what happens when k equals to 2, what happens when k equals to 3. We have all discussed this, so you can refer to the last sessions. So now what is inertia versus Shillaughter? So inertia measures the compactness and Shillaughter actually measures the compactness plus the separation. Okay, so inertia actually always decreases, but Shillaughter has the best peak. So for inertia, we use the elbow method, and for getting the evaluation, we use the Silhouette. Okay, so that is the idea. Now coming down to the code, here basically what we are trying to do here, we are just like taking the value, like we are just trying for k equals to one cluster, calculating the inertia, then moving down for k equals to two cluster, calculating the inertia. Like we are keeping on doing this till the value of k equals to 10. Next, we are storing all inertia value. Then later, what we are doing, we are drawing a graph to find the elbow point. Okay. Now, this is what we are doing. So, inertia we are taking as like creating a elbow box to like empty box, sorry, creating an empty box to store the numbers here in case of inertia, this one. And then what kind of box it is? It is a list, right? So, we are taking an empty list. Now, why we are doing this? Because we need to remember the inertia from k equals to 1 going down to k equals to 10. So for comparing, we need to take an empty list to just compare it later once we get all of the whole loop will work for till 10, like till from 1 to 10, then it will stop. So for all of the values needs to be stored somewhere. That's why we are taking it round. Okay. So for k in k range that we are taking up, so that is first it will go for k equals to 1, k equal to 2. Last time it will go for k equal to 10. So Km equals to K means n cluster equal to K random state 42. That simply means that create a K means machine with K groups. K means that is creating a cluster model. N cluster we are taking as K. So that means number of group for the current value of k. If k equals to 3, it will make 3 clusters, and random state equals to 4. That means it starts from the same point every time. Without it, the result may vary or change. So with it, it will stay same. That's why we are using it. So we are using km.fit, and we are using x scaled. So what does fit means? That look at data, find the cluster center, and assign the point to the cluster. That is what it does. And x scale is not equal to x. Why it is? Because x mean uses the distance. So we are using the scaled, this one, x scaled we are using. After scaling the data or x value we are getting, that we are storing it. Now, inertia dot append that we are using in km dot inertia. That simply means like we are saving how messy the clusters are. Okay, so km dot inertia, that is inertia value after training. That is the value. Okay, so now what does append do? It actually adds the value to the list one by one. Okay, so this is how it goes, and then we are just plotting it down. So you can see the plot here. So here, basically, we have got the value from k equal to 1 to k equal to 10. For each k, we calculated the inertia and taken it accordingly. So figured plt.fig fig size 8.5, 8,5 that creates the canvas for us accordingly. Okay, then plt.plot k underscore range comma inertia marker o, that simply means draw a line graph with dots. Okay, so next we have k range that goes from x-axis, values are coming as 1, 2, 3, going down to 10. Okay, so this is how we are going. So now you can see the plots are like from first k equal to 1, it is have a huge drop till k equal to 2. Then we have a like stabilization, a bit lesser drop in k equals to 3. Then a huge drop at 4 and equally it is taking. So we are as of now considering taking the value of k equals to 3 because after that there is a drop and it is the data is getting more stabilized. So now we are training it using that. So after that, you can see we are training it. So k means equals to k means for n cluster 3. So the same thing we are doing here. So we are already deciding the base number of clusters we are getting as 3 from the elbow method. Now we want groups of all flowers in 3 groups and say which flowers belong to which group. Okay, that is what we are doing up here. So after that, basically we are taking here the same way we are taking cluster 3 random state for 42 and we are doing k-means dot fit predict that we are doing. So that actually learns the group and add them and tell them which group each flowers belong. Okay. So fit x scaled, that part actually is for the scaling part of it. And predict x scale is the labeling basically. Okay. Predict x scale, this part is basically the labeling section. And fit predict that is the shortcut. So that's why we are using fit plus predict into like together we are using it. Okay. So clusters we are getting in the clusters df cluster equals to clusters. So we'll get flower 1 cluster 0, flower 2 cluster 3, flower 4 cluster 1. Like that we will be getting. So here it simply means adding the cluster numbers to the table. Okay. So that is what we are doing. So basically after here, if I am just going and doing df dot head and let me take it. So here you are getting this part. This is how it is coming, and then we are getting the clusters here. We are getting the clusters here. Okay, this is how it will come up. Okay. Now this is the sections we have already discussed. Now we are going for the plot. We are using here what we are using. We are drawing a small graph for each graph to compare with two features at a time, so that we are getting it accordingly. So when we are getting with the clusters like the sepal length with the actual levels, this is how it is fitting. Sepal length with the actual level, this is how sepal length with the petal width, how it is printing, like all of the comparative plots we have plotted it all together. Okay. Then if you are going down, we are using the PCA basically here. So what we are doing in the PCA section. So here we have just taken PCA. So PCA is the principal component analysis. We have already discussed about it. So PCA is the PCA machine and n components we are taking as two basically here. And why two? So that we can draw a graph on x and y axis. That's why. So we are just dropping down the dimension to two dimensions so that we can just plot it accordingly. So xPCA equal to PCA dot fit transform x scaled. So fit is the PCA study of the data and finds the direction with maximum information, and transform actually change the data into two new features. So xPCA is the new data set that has the shape and the number of flowers, that is 2. Okay, that is how we are getting it. Now we are going for the plt.figure where we are getting like the all of the parts we have taken, and now in the figure you can see these are the plot. K means cluster. We have got this is how we have got the plot. Okay. Now, after all of it, we have just gone ahead with the Laute score. So basically, Laute score tells us how happy each data point is inside its cluster. So happy means good cluster, confused means the bad cluster. Okay, so that is what we have taken it here. So we have taken it like that and printed the Laute score. So the Laute score is coming out 0.47. So we are not that happy with that with this value. So we want to just get it better, because if the value is around from suppose it's 0.5 to 0.7, we can consider that is the model is okay, like applicable kind of. But we want a good model, right? So that's why we want to take it in that way. So similarly, what we are doing here, so here basically we want to just we are just writing like here. I have not just changed that part there. We have just redone all of it so that you have the idea what is the like where how we can just improve the Laute score. Okay, so basically, here the logic is like in my current situation, I have used k-means and I have got this Laute score that is 0.48. That means the classes are decent, right? But not perfect. So, what things can improve this Laute score? So, we can scale the data properly, we can reduce the noise like using PCA. Next, we can visualize the cluster clearly and then go for check for accordingly. We can choose a better value of k and check the separation using matrix. Okay, this is what we can do. So what we will be doing, we will cleaning the data, compress the data, cluster better, then we will be measure the cluster quality, then we will be going down for the visualizing and compare the result. This is what we are doing. So we have just gone for importing the libraries, all of the necessary libraries we have imported. Then again, the same stuff we have then loaded the iris data set, considered the variables as x and y, created the data frame and created a new column that is the actual label where I'll get store the value of y. Now we have done a feature selection here. Okay. So why we are doing this? The iris data set has four features: sepal length, sepal width, petal length, plotel width. But not all features are equally useful for cluster, right? So petal features separate the flowers much better than the sepals, right? Petal features are doing it better. So we are just doing a feature selection up here. So in real life, suppose we have the color, size, weight, smell. If the color and size are enough, we will use why we will be using this smell part or the weight part, right? So that is the case here. So here we are using X select that is equal to DF petal length CM comma petal width. So we are choosing this is the selection part that is going on from the big table. We are only picking the petal length and petal width. In the previous for the previous model, we have not performed this section of feature selection. Okay, so this we have done. Now going down, we are going for again the standardization. So again, we are just doing this the same way we have done the standardization. We have not taken it. Just here we have not used not used the X altogether. Here we have just used the selected features of petal length and petal width. Okay. So this is how we have taken. For this, we have done the standardization, then gone ahead similar way with elbow method. And here we have just taken n innate equals to 50. Okay, so here basically we have taken n innate equals to 50. That means it will just go 50 different starting points to avoid bad random start. Okay, so that is what it will doing, like tossing the ball into the basket 50 times and choosing the best throw, right? So the same way we are just choosing it like that. Okay, and then we are just plotting it. Now you can see the plot, we have got a better plot up here. Like here, if you can see the plot, elbow plot, it is a bit haphazard. Like from here, we have taken it 3 because there is a sharp fall, then it has came up. But we could have taken 4 as well, right? That is also accordingly commendable. But we have taken 3 because it has just taken it a bit, like it has just taken a point, a left here, like a lesser change we can see from this to this. So that's why we have taken it 3, and then there is a fall a bit, right? So that's why we have taken 3. So, but here you can see a better understanding you'll be getting. So from 1 to 2, there is a very sharp fall. 2 to 3, there is a good fall, and from 3 to 4, the transitions are going quite similar. That's why we are for sure taking the value of cluster k equals to 3. The value of k we are taking it as 3. Okay. After we have just get the understanding accordingly, so we are just going further accordingly. So we are just going for PCA. So here what we are doing, so our data, that is X scale, has two features now, that is petal length and width. Sometimes the data set has four features like 4 or 10, but humans can only see the 2D graphs, right? So we are using PCA accordingly, so that we can just plot it accordingly. So here we are using PCA equals to n components 2, that is we are keeping two main directions for plotting, even if the original data has four features. We know the compress is 2 while just keeping the most of the information intact. So X PCA, that is PCA dot fit underscore transform. So fit is the learning direction. So PCA looks at your data and find the direction with maximum variations where the data spreads more, and transform is the compress that converts the original two features into two new features. That is, each one row is equal to one flower. So each column would be one principal component. Okay. So that is how we are taking it. So after that, we are going for taking the train optimized K means model. So here basically we already have the scale and the compressed data, that is XPCA. So we now want to group the flowers using K-means. Then we will be storing the cluster numbers in the table, that is DF, and later we will be using the clusters as 0, cluster 1, cluster 2, like this we will be using. So why we use PCA here? Because PCA keeps two main direction, makes the cluster easier to separate visually, and keeps the Silhouette score, like helps Silhouette score because the clusters become clearer. Okay, that is the case. So here we are using n cluster equals to 3. So we want three groups for Setosa, Versicola and Versinica, three different groups. Random state we have taken 42, that always start from the same random position. So the result are the same for in the each time. And in it we have taken 50. That means we'll try 50 random starting points and picking the best one. And max iteration, we will go for 500 iteration, that allows K means to move cluster centers up to 500 times to find the best position. Okay. So next we have used cluster equals to K means dot fit underscore predict X PCA, because PCA1 we have taken it before, that we are just going further. So cluster is like the list of numbers, that is 0, 1, 2, 0, 1, 1, 2, 0, like that. So each number is cluster assigned for each flower, and DF cluster, that is equal to cluster that adds a new column to the table showing which cluster each flower belongs to. Okay, that is what we are doing up here. So why this why this actually improves the Silhouette score? Because we are just doing the hyperparameter tuning here. We are changing the parameters that we have in hand in changing by human, right? This we have taken 500 iteration, we have taken 50 in it, right? This is we are taking from our end. So this actually using the selected features, that is petals, that is that has the less noise. Scaling has made it a fair distance accordingly, and PCA is the best 2D separation that we can have. Init and init equals to 50 and max iteration 500. That is better for cluster centers. So that is what we are doing. So k-means actually assign each point to the nearest cluster center after the smart preparation we have done. So this is the part. Now we can go down for the Silaute score. So here what we are doing, we are measuring the Silaute score. Silaute score measure how happy each cluster is in the centers, right? So after doing all of the preparation of X selected, X scaled, X PCA, X mean with N init 50 and max iteration 500, we are getting the better cluster centers here. You can get the Silaute score is better than before, far better than before. Now we are getting at 0.67, right? So the Silaute score is doing good here. So we are getting a kind of good Silaute score up here. Okay. So this is what it is. Now we are just going for cluster visualization. So here basically we already ran the k-means on PCA, reduced data. So each flower now has the cluster number. So we want to see the group on the plot. That's why. So you can see it is giving a better cluster plot. So this is the plot now, and before let me just check the plot. So this was the plot before, and like you can see, the plots are not coming in a correct format. Now, if you can see, the plots are coming better. The segregations are better, and the plots are coming more in a like the clusters are more clearer, right? So this is what we have done till here. Now we want to map the cluster with the actual labels. Okay, so we want to map it with the actual labels. That's what we want to do. So clusters we have taken and we have map labels. Now we are just going for this for loop and taking it all together. And after that, we are checking for the accuracy of the model. So the accuracy of the model is going around 96%. That means the model is doing very good. Now we have, according with that, we have just gone ahead and plotted the confusion matrix, and here you can see the confusion matrix. This is how the values are coming. So here we have got the predicted value, and these are the true values. So majority values are true. So here we are getting a bit a problematic part, and here a bit problematic part. Rest other values are going good. Okay. So rows are the actual flowers, columns are the predicted numbers, and the numbers are the count of the flowers that are getting. So 50 is setosa that we are correctly clustered. 2 vesicola got mismatched as versinica. You can see 2 has got mismatched with versinica like that. And we have got the 48 correctly predicted for vesicolor, and versinica 46 was correctly got. Okay, so this is how we have just plot the confusion matrix. Now we are going for AOC ROC curve. So this is the AOC ROC curve. You can see this green signifies the Visinica. That means AOC is 0.51. Blue one, like this section is basically for Setosa. That is AOC is 0 for it, and Versicola AUC is 0.52, that is this yellowish one. Okay, so this helps to give a clearer picture beyond accuracy, help us to understand which flower type are confusing. Okay, so this is the part we have discussed. Now we have got a clustered centered heat map. Okay, so we have got this cluster centered heat map here. So here basically we have got the distance from the k-means cluster. So k-means actually find the centroid for each of the cluster. So each flower has a distance to each centroid, smaller distance the flower is closer, more distance, that means likely beyond to other cluster, right? That converts the distance into score and binarize the actual labels. So here you can see the values accordingly. So this is how the plots are coming. So this is all about the k-means with improve. Like here you understood about cross validation, you have understood about hyperparameter tuning, what are the necessary steps that needs to be taken to improve the Laute score. I guess all of this you have understood till now. Okay. Now we will be going ahead here with this hierarchical clustering and all. So after this section we will be just going down here and understanding about the hierarchical clustering and the dendrogram. So basically here we have what we have taken. We have like we understood about what is hierarchical clustering in the last session. If you don't like if you don't remember, just refer to the last to last sessions. Okay. So hierarchical clustering is a way of grouping like similar points together step by step. Okay, so that is what it is. So now we have here the array accordingly, and basically here we have just imported the numpy. Then we have imported the dendrogram linkage. Then we have just imported the matplotlib accordingly. Now we have just taken the data set numpy array. We have taken 1.2, 1 comma 2, 1 comma 4, 1 comma 0, 4 comma 2, 4 comma 4, 4 comma 0, like this we are taking, and Z we are taking linkage X comma what. Okay, so that means it is telling the computer to combine points into clusters. So linkage is like calculate with points on clusters that should combine each steps, and what is like a rule that keeps cluster as compact as possible. So how what method works here? So we calculate the distance between every pair of the points and then combine the closest pair first. Okay, and then accordingly we move and we recalculate the distance between the new point and the other points, and then repeat until all of the points we are getting are combined into one big cluster. Okay, this is how we are moving. Now we are getting dendrogram Z. We are plotting the dendrogram. So here you will get the dendrogram here. So you can see it is hierarchical clustering. That's why we are just taking it like initially we have taken it like that. So first we have paired 3 and 5, 0 and 1. With 3 and 5 we have paired 4. With 0 and 1 we have paired 2. And accordingly we have paired this sets together. Okay, so that is what we have taken it. Now we will be going ahead with agglomerator because it is a type of hierarchical clustering where it starts from all of the point being the single one, and then usually it groups it together. Okay, so here you can see the plot. So basically here what we have done, we have imported the libraries, then we have gone down with the model, like we have gone down with the data, then we have created the agglomerative clustering model. So it creates the clustering model and tells like n cluster equals to 2. So we want to find two final clusters, and the matrix we are using the Euclidean, so that the distance should be measured using Euclidean, and linkage we are using again what linkage that merges the center to minimize the variance inside the cluster. Okay, so that is what it is doing. And coming down later, we are using labels equals to model.fit predicts. So that let the model look at the points and decide which cluster each point belongs to. So label equals to array showing the cluster numbers on each point. Okay, so the labels is equals to 0, 0, 0, 1, 1, 1. So first 3 points, the clusters are going for 0. Then again, suppose the 3 points we are getting, the clusters are going 1. So this is how, like I have just given you an example. So this is how it should come. Okay. Now we are drawing the point on the 2D graph here basically. So basically we are getting x 0 comma we are getting is 2 comma 0. That means we are getting x coordinate, and x is 2 comma 1, that is y coordinate. Okay. So C labels, that is color points according to the cluster assigned. C map where it is, that is the color palette, and S equals to 100, that is make 100 the makes the point 100 times bigger. Okay, so that it can be viewed. Now we have just taken plot title, X label, Y label, and shown that this is how my plots are looking. Okay, so this is the agglomerative clustering. Now coming down to the hierarchical divisive clustering. So divisive clustering is like we start from a group and eventually divide it to the single one, like split it into the clusters. Okay, so basically here we have just taken the imported the libraries, then just taken the data points. Then here we are using k-means. So we have created a k-mean models to split the bigger cluster into two specific clusters. Okay. So we have used k-means the same way the previous one I have showed you. The similar way we have used k-means. Then we have got the labels. So based on that labels, we will be getting the clusters, and then we have just plotted it down. The same thing we have taken, like the same kind of the variations we have taken for agglomerative, the same we have taken here. But just we have just changed the title, that is hierarchical divisive clustering, and the first split we are seeing, that see we have seen the first split. This is the split that we have brought. There are two clusters. Yellow comes under one cluster, and this magenta or brownish color comes under the second cluster. Okay. Now there is another algorithm called DB scan. We had to discuss about DB scan. So DB scan is density-based spatial clustering for applications with noise. So it actually groups point based on how closely they are on like they are to many other points basically. Okay, so that comes as that is basically based on density. Okay, so here the core idea comes with the core points, border points, and the noise points. So we have the cluster that piles of sand where we are getting the grains, as it how it is moving, the clusters are moving like that in case of DB scan. Okay, so the similar way coming down to the problem, we have just imported the all of the necessary libraries, taken the data points, and created and applied the DB scan clustering model. So here basically we have taken it accordingly. So basically, you can see here we have used EPS equals to 3. EPS is the radius to look for the neighbors, and mean sample that is equal to 2. So that is the minimum number of points to form the dense cluster. Okay, that we have taken, and then we have gone for the visualization, and you can see the visualization is coming up like that. So this you can see coming down as a similar clusters. So 3 points are coming here. So basically you can see how many points we have taken, 6 points. So three similar kind of points we are getting here. There are 2 points which are yellow in color. They are like close to each other. So put in another cluster, and this is far separated. That's why it is blue in color. So this one you can see, this one is can be different from the other one, other points. That's why we are taking it like that. So this is how we have taken it. Another one, we have the mean shift clustering. The same way we have taken the mean shift clustering. Basically, what happened in mean shift? Mean shift is finds the dense area, that is the fix in the data, and forms the cluster around them. So it looked at each of the point and its neighbor within a certain radius, that is the bandwidth, and move the point towards the mean, that is the average of the neighbors. Okay, and it repeated until the point coverage to the dense area. That is the main idea. So the similar way we have taken it, just like the other one, we have just imported the necessary libraries, and then like taken the data points, and then created and applied the mean shift model here. So mean shift, we have taken the bandwidth as 4. Bandwidth is the radius to look around each of the point to find the radius. That is the bandwidth. So we have taken it 4, and we have just got mean shift dot fit. So that actually run the algorithm. So each point shift towards the nearest dense area. Okay. Then we have got the labels equals to mean shift dot labels. So it which actually gets which labels in each of the points belong to. That is how it is actually taking it in that way. Okay. And then we are just visualizing it. So you can see this is the visualization and these are the cluster centers. This cross are the cluster centers. So these are all about the different unsupervised clustering algorithms that we have discussed. So this is all about the clustering part of unsupervised. Okay. So from the next session, we will be moving down in the form that we have to go for the neural networks. Basically, we have to just make sure and make understand about the neural networks, how neural networks work, what is the correlation of neural network with the biological neuron, how they are connecting. So what is the perceptron, what is the single layer model, what is the multi-layer perceptron, how things work accordingly. All of this we will be understanding in the like we will be continuing from the next session, and one by one we will be taking care of all of it. Okay. So thank you guys for connecting in today's session. We will be just rejoining in the next session, reconnecting actually in the next session, and we will be continuing with the neural network. Okay, that is coming under the deep learning. Deep learning, that is the advanced part of machine learning and comes under the deep learning area. Okay. So thank you guys. Thank you for connecting in today's session. Bye.